Vectors. Vector is a quantity that has both magnitude or length and direction. That's what exactly was the joke in the movie. Vectors have both direction and magnitude. Magnitude basically is length, or how big the vector is. So the idea is, here's how we draw it. The vector has the beginning, sometimes they call it the tail, and the end, sometimes they call it the head, and then it has a direction. That's why it's pointing somewhere. And then it also has a size, and size is the magnitude. Before we were working with segments, we would say, oh, this is the distance from A to B. Well, distance from A to B would be the same as distance from B to A, so there was no direction. Now there's a direction, like so or like so, and we're going to be working with that. So now we'll be pointing like so, or pointing like so. Direction and the size. That's the definition of a vector. Our job is to learn how to draw vectors and work with them. So this is the beginning of a huge chapter. 10.1 was just introduction to 3D coordinates, but chapter 10.2 is actually where it gets very interesting and important. How to draw the vector. Notation is A, tiny error, equals these kind of brackets 2, 3. That is a notation. As you can see, sometimes in the book they don't have an arrow. That is wrong. It's not a mistake, but that is not polite not to put anything. Two notations you will see around the world. Is there just a bar? That's because some people were lazy to find the little arrow in the code to code it. Or the little arrow is better. That's international notation. The shape of the brackets is extremely important. We will have to destroy all your bad habits this semester from high school, which when you just randomly put something like this, or then you change your mind and you put like this, then you have like this. No, all of this have meanings actually in science. And also I can see 5 times 7. That's a big no-no. The cross is a cross product. In this class we're gonna learn about that. So I will have to teach you the mathematical literacy so you can actually be accepted to the mathematical, physical, engineering society with knowledge of what notation means. And also it's isn't fascinating, it's the same around the world. So you should know that. So how to draw that? Let's do it in 2D. Y and X. In 2D first, because it's easier to imagine. Vector A has 2 and 3. That means X is 2 and Y is 3. That means I will move away to 2 points to the right for X and 3 points up for Y. That means I'm pointing 2 units to the right and 3 units up. So I see it like this. The vector will be from 0, 0 to this point. And the point will be P parenthesis 2, 3. Very important. Parenthesis is a point. Brackets is a vector. What this tilted pointy brackets. Pointy brackets is a vector. Straight brackets is a matrix. So there's lots of different notations. Determinant of the matrix actually. So this vector is pointing to the point P, 2 and 3. 2 to the right, 3 up. In 3D, it looks like this. See, it's taken from American book. That's why it's tilted like so. But actually, it's supposed to be X goes to the front, Y goes to the right, like so. But okay, it's fine. So X, Y, Z, draw this quickly. And then P with A, B, C. That means A units towards X, B units towards Y, and C units towards Z. That gives me a point P in 3D. That gives me a point P in 3D. Basically, intuitively, when it's only 2 direction, it says, oh, I'm pointing towards there on x-axis, but also Z will be a bit higher, so it moves it up. Oh, don't forget to tilt it to the left or right on y-axis, so I'm tilting it. So it's literally a pointer. And we're tilting it depending on the coordinates of the vector. Make sense? The inputs of the vector are called components. Components of the vector. Here it is. So please write this down. The vector v, see either a bar or a little arrow. Arrow is better actually. The vector v with tail at 0 and head at the point P, A, B, C, is called the position vector of the point P, and we write v equals brackets. We call A, B, and C components of the vector. That's the definition. If it starts from 0 and points at some point, it's called a position vector because it points at some position from 0, 0. So 0, 0, 0 is kind of your pole, your node, your center. Then from that center, you point at the fly. Or like last time I was trying to tell you how fly is flying in 3D versus the caterpillar was just moving up, down, left, right. So the fly is flying and you point with a finger. That's exactly what vector is. From the center, which is you, for example, you point. That's called a position vector. You point at the position of the point in 3D. Too fast? No, yes, let me wait a little bit more. Okay, looks good. Let's practice drawing the 3D one. That's harder. C is a vector. C is a vector. 2, minus 2, and 5. Remember tilted brackets, pointy brackets. That means we need to have 2 units on x-axis, minus 2 units on y-axis, and 5 units on z-axis. So, by the way, last time I made a mistake, and then we completely moved on. Maybe I made it on purpose, maybe not. And nobody pointed out. And then someone pointed out, but was too humble to point out in class. Well, you should not be shy. You should point out. That's kind of the whole hobby of this class. Catch the instructor mistake. It's very important. Not only it makes good notes, but also that's kind of makes it more interesting. You pay attention, you catch my mistake, and then you feel satisfied, right? You should do that. I highly encouraging that. And I don't want to have bad notes, so you better point out. 3D, x towards me, y to the right, z up. That's positive ones. And then, of course, you can draw dash, 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 down and back, like so. 0 at the middle. That's how quickly we draw 3D coordinates. 2 units to the x. That means 2 units to the front. So I'm going to go 2 units towards me. Here it is. 2 units, but negative. So to the left instead of the right. So I'm going to go the same distance, but to the left. 5 units up. That's pretty high. We go 5. So usually you imagine it like so. You first draw a vector in 2D. In 2D, you see, it will be somewhere in between, right? So if it's 2 to the front and 2 to the left, because it's negative, then somewhere in between, and then it's lifted up. So from the center, it goes up and points to this fly over here. Fly, maybe it's too long actually. Goes up to 5 units. In 2D, it would stay on the floor between x and y. But then we're lifting it up. That makes it 3-dimensional. And it points at the point P, parenthesis 2, minus 2, and 5. Again, nobody emailed me about colors. So I will be using colors unless you change your mind. Let me know if you don't see any colors. Oh, we should have practiced the lights. Is this better? I always ask about that. What is happening? Okay, I think this was the best. Questions about this? This kind of first drawing, classical drawing of the vector. Oh, maybe to point out, V, little r, equals pointed brackets 2 minus 2 and 5, pointed brackets. That is, maybe I will change the color, this arrow, that's the vector. And vector points at the point, and that's why we call it position vector. It points at some position. Make sense? So pointing at things apparently makes the science much harder. What is the rate of change of something if it has a direction? If you point this way and completely the opposite way, are they gonna cancel each other out? And so on. So that's what we're gonna be learning today. The segment was so simple. When you add pointing things, somehow it immediately makes it much more complicated. It adds more dimension to it. Applications, you don't have to write this down, just to make it more interesting. The world of vectors is filled with applications. To be honest, any major you choose, you will have vectors here. Like the moment, right now you're sitting here and you're breathing. You're making a vector field of the temperature that comes out of your mouth. The temperature of your lungs and stomach is changing when you're breathing. That is vectors. The blood circulating in your body, that is a vector field, which we call flux, vector flow. And then the vectors are going one direction, but if they stuck at some point, now it's tend to have, you can have a cardiac attack and so on. All of the science is done using vectors. The whole world is made out of vectors right now. The light you see from the projectors are vectors. And automatic cars are driving on the streets. They're using vector fields. Electromagnetic, of course, fields, black holes, everything, you name it. Surprisingly, AI as well. We were doing project last semester and we learned AI, trying to create image from reading or write down what it sees from the image using vectors as well. The simple one is walking. That's from 2D. A velocity vector represents a direction and magnitude in which a person or an object is moving. If I'm moving 2 units to the right, then I will say A has 2 units first. Then the other 2 units, that means up. So the total will be diagonal, right? That's my vector A. I'm moving, if I wanted to move 2 units to the east, and then 2 units to the north, right, and up. Then now I'm moving northeast. That's the idea here. What's the funny little phrase you guys have to memorize? North, east, south, west order? Don't eat saggy waffles. It's like the funniest thing I've ever heard. I only learned last year. Don't eat, never eat north, east, south, west. Yeah. I don't have that one. I just memorized it. So again, like somehow in my culture, we don't have a song for the alphabet, nothing. We just memorize it. But you guys have funny phrases for everything. Very cute. Never eat saggy. And there was one more. There was worms. Ew. Why would you eat worms and saggy worms? So that is the idea. East, north, northeast. That's basically, instead of walking towards the path they gave you, you go through the grass, right? That is what they mean here. There's a direction. You're going that way. Now, the force, of course, the gravitational forces and everything. The force that an object exerts on another can be represented by a force vector because it has a direction. Force has a direction, so it's a vector. Gravity, for example. In engineering, if the force acting on a bridge and is too big, the bridge might collapse. So gravitational force is now, if when you jump, you're fighting the gravity and actually it goes the opposite direction. So the magnitude of the strength of your jump matters. If you jump really high, then it will be good. If you jump a little bit, you'll come back fast. Magnetism and electricity, of course. It appears in economics as well. If you want to see the trend of the company, here's the trend of the company. This is a vector, no explanation. Can you understand what it means? It means that, so this is the beginning, this is the end, right? This is the beginning, this is the end. Apples on the x-axis, bananas, selling bananas on the y-axis. Seems like we sold more bananas than apples. Do you see that? So if it's exactly going to be like so, it will be equal bananas and apples. If it's like so, no bananas were sold, just apples. So this represents something as a trend in business as well. So this is a current trend for company to produce more bananas and apples. Make sense? So that's how the tiltiness tells you about that. The slope, which we're going to talk about soon. My favorite and very intuitive way is this one. I found it accidentally and I like it. So a mom having 3 kids, which one looks like a potato? I don't know why. I don't know why. But it's like twin brothers and a potato. So she looks very happy, as you can see. And they are pulling her different directions. So we're going to have to figure out what does it mean to have different vectors from the same point, right? So intuitively, now you see what it means. the mom is being pulled to the, so for example, mom is a center, right? Pulled to this way by one twin and then to this way by another twin, maybe with the same strengths, maybe not. Usually one twin usually is the evil one, right? So it should be stronger, I think. And then one is pulling down, so she cannot just move that fast. So where are they gonna be a vector? So obviously she's not gonna move here right away because there's another force pulling on the other side. She's not gonna move here either. She will move somewhere in between them all, right? If she's like falling, she will fall somewhere in between. And that's exactly what vector is. The vector has a direction and a strength, and the strength depends on how strong the other ones. Those other ones are indicated as components of the vector. Let's learn how to add, subtract, and multiply vectors. Multiply for now by number and then between each other. Basic operations. Write this down. This is a good topic. Basic operations. Now, I don't know. I guess let's write this down. But I just like the visualization of this. And I know the students appreciate visualization a lot. Many of us are visual learners, so I try to visualize everything. This is a definition of the sum. Let's write it down. If U and V, so my Calculus 3 students from a year ago complained that we should stop using U and V all the time because they look the same from the distance, right? But then ironically, that's the most popular vectors in scientific articles. So because of they complained, well, they just politely told me that it's not convenient. I started switching to others. But as you can see, most books use U and V. If U and V are vectors positioned so that initial point of V is a terminal point of U. Terminal means the end, right? Then the sum, that's the most important. We're trying to figure out how to add vectors. Has a definition, is the vector from the initial point of U to the terminal point of V. As always, I give you all these notes, just letting you know. And then don't draw the pictures yet. I'll have to show you how to draw them so you will understand better. It says something which is more complicated than actually it is. So I will show you how we see it visually and you will get it. This phrase always confused me in any language. It's kind of too complicated. Visual is much easier to understand. So I requested lots of photos in the forum and nobody posted any photos. Where is your baking? Where is your paintings? Where is your horse? We have a person here who rides horses. You bragged about some hobbies. Now there's no pictures. Like, how is it possible? So I commented a lot. You should post something. So if U and V, let me wait a little bit more. If U and V are vectors positioned so that initial point of V is a terminal point of U. Let's see how it looks like. I have a vector U. It goes like that. And then there's a continuation vector V. So it starts at the end and goes somewhere else, doesn't matter where. What will be the sum? U plus V. Well, the sum will be starting at the beginning and ending at the end. That's what this whole phrase says. It's just too complicated. But that's the idea. Starts at the beginning, ending at the end. That's called a triangle law. That makes sense. Again, instead of walking the way they gave us this path between buildings, you just walk through the grass, right? That's a sum of two walks, and it seems like better. So instead of walking normal way they gave us between buildings, you just do a shortcut and you go through the grass. That's kind of how you can see it. That's the sum of two walks. Then there's a parallelogram law. What if they are not connected like this? What if it's not a continuation? If it's continuation, it makes sense. Some force was pushing me to the right, another force is pushing me up, so the total force will be somewhere in between, to the right and up. That's kind of intuitively makes sense. But what if that's not the case? So let's check the second case. What if the U vector points to the right, and then the V vector is not continuing it? It's actually pointing somewhere else. But they are started at the same point. Intuitively, the resulting vector will be somewhere in between, right? So just like a mom was pulled to the right and to the left, right? So somewhere in between will be she is pulled somewhere to the middle. But where? 45 degrees, 75 degrees, hard to figure out. So they build a parallelogram. They copy v vector on top of the u vector to kind of recreate the same situation as before. So they want to continue. And then they copy u vector at the end of v vector. That creates a parallelogram. The diagonal will be the answer. The diagonal from the beginning, the diagonal vector has beginning at the beginning and end at the end. So they all pointed to a point. They all went out, in. So the sum will be the one in the middle, which again, imagine forces. The kid is pulling to one side, the kid is pulling to another side, and then the sum will be somewhere in where do you fall? You're falling somewhere in between, on the potato boy, on the potato kid. Unfortunately, I just realized that. Actually, like if she will be actually falling, then that's why he looks so scared. Because I think if she falls on the potato kid with a cute scarf. You see, he has a scarf. Look at this. Let me just zoom in for you to see the picture. Oof. What is the point of this potato baby? So, that's called parallelogram law. Do you know how to say parallelogram in Russian? Parallelogram. It's very complicated. What do you think about that? Ask me. Questions, ideas. Don't fall asleep at the back. Are you guys okay with the back? Can you hear me well? Yeah, thank you for the thumb up. Nice. Because I can't yell louder, but then people front will get scared. Now, let's write down how does it work in the writing form. Addition. Addition of two vectors or more, doesn't matter. Addition of vectors is if I have a vector given, let's practice writing vectors. V equals, and it has A, B, C as components of the vector. I see I do V and U all the time. Okay, let's switch to F. You see, very interesting. I will show you something. F is M, T, and G. If I don't put a bar on top of the F or an arrow, that becomes a function. So that's bad. It's bad if you don't put anything. Either put a bar or a vector is even better. Then you know it's a vector. It's reserved for the vector notation around the world. Soon we're going to learn a vector function, which will be a function and a vector at the same time. So it's going to be pretty cool too. Given this, let's find V plus F. V plus F, sum of two vectors is a vector. Not very obvious. Soon we're going to learn that the product of two vectors can be a number and a vector also. We're going to call it vector product and number product, which is a scalar product. So that is a stupid comment from the first point of view. A vector plus a vector gives you a vector. But soon you will learn it's not always the case. It depends on the operation. And then you add corresponding components. A plus M, T will be B plus T, C plus G. That makes sense. If one vector was really, really tilted to the left, that leftist component will tilt the total to the left too. That is the idea. If the other vector had zero tiltedness, then everything will be tilted to the left because the first one moved it to the left. So the sum basically adds up corresponding components. Now, we also can multiply by a number. That kind of makes sense. If A is given as 1 and 2, then let's find 3 times A. See, if I keep A without nothing, A can be a function, A can be a constant, A can be a vector. Too complicated. So to make it easier for everyone, this notation matters. 3 times A is, we're basically multiplying 3 by the vector 1 and 2. So now there's a question how to do that. Well, it's you just multiply component by component. Each component grew 3 times longer. So now it is 3 and, should I write down? Let's do once. 3 times 1, 3 times 2. So the new vector now is 3 and 6. That means if the kid was pulling you with 3 and 6 to the right, and then another kid joined, that's a multiplying by some force, for example. 3 times stronger. So now it pulls 3 times stronger to the same direction. That is important. The important part is to visualize that original A looks like this. The new A will be exactly the same direction, but 3 times longer. A, 3A. So you can extend it or shrink it. That's basically changing the magnitude, changing the size of it. Guess what happens? Okay, let me ask you how to create from A minus, how to create, we multiplied by 3, we improved the lengths, the strengths of that field, magnetic field, or whatever that is, by 3 units. But what if I want to reverse it? What if I want to be the same one, but the opposite direction? What do you think I should do? Multiply by negative. It's kind of totally common sense. Minus A. So let's do that. Minus A will give you exactly the same vector. It's still 1 and 2, but now it points to a different direction, so it's going to be minus 1 and minus 2. Same strength, but the opposite direction. So it have to be same length. And so on. Here's the visual representation for you. Let me move it up. Visual. Whatever I just showed you, you don't have to rewrite it. A had the original size, 3A the same direction, but 3 times bigger. 1, 2, and 3. 3 times bigger. Then minus A is the same one, but going different direction. Minus 2A, for example, will be twice bigger in the opposite direction. So just some visual understanding of the situation. What do you think about that? Move on. Subtraction of vectors surprisingly is harder than addition. You don't have to write this down. That is too complicated to explain in writing. Easier to show. But basically, we define the negative vector and add the negative vector. Same idea as we did in school, like whatever, middle school, you name it. Instead of 2 minus 5, we're defining 2 adding minus 5. That's how you explain subtraction by using addition. That's common sense. So we're going to do the same thing with the vectors. So that's what we did before with numbers. With vectors, it's going to be, instead of A, they do it V1, V2, I don't like it. Let's have it A minus B. Let's write this down. Will be shown as A plus negative B. So we're reversing B and adding it instead of subtracting it. So that's the idea. Now graphically, it's not very obvious though. Graphically, it's kind of awkward. So that's somehow people get stuck with subtraction in vectors. Let me show you why. So we have A. So draw this. We have A. And then B continues A. That's a triangle rule. We just learn it. A plus B. So A and B. A plus B starts at the beginning, ends at the end. That's what we just learned. So A minus B will reverse the order. A minus B will point... let me draw it separately. I think it's better this way. While subtraction is A goes here, B goes here. How to know how to subtract? You do it this way. You always have the positive, that's the positive one, to be pointed at. Let me choose another color. So the subtraction points to the positive one. That's how I like to memorize it. So the negative one is the beginning because it's smaller. That's not true, but that's kind of mnemonic way to remember it. And then the positive one, you point at the positive one. You point at the positive one. So when they are starting at the same point, that comes from the triangle rule again. Basically, what we do here is when you want to add minus B. You take your B, which is here in blue, and change the direction, right? Now B will look down like so. Now we have B and an A continuation. The sum of that will be A minus B. So it always points at the positive one. Yes?
In addition, how do you determine which vector goes first, I guess?
Yeah, the graphing is the confusing part. I do understand the question, I think. You can move them around. So since they're parallel, we're gonna learn that you can actually relocate vectors. Even if this one is here and this one is here, you carefully, actually I can show you. You carefully move one vector and then connect them together. Now, the one that is negative, if A minus B is given, right? We're trying to find A minus B. So if this is A, it will point at A. That's my point. That's how I memorize it, at least. And it makes sense because B is positive. To make it negative, I'm reversing the order. Now it's minus B. Now it's exactly what we learned as a sum. A plus minus B will be beginning at the beginning and at the end. So this explanation also makes sense. In both ways, the explanation makes sense. Either it points at the positive or you just learn it from the sum. Yeah, just a second.
Can you, for subtraction, you still start with A and then make B just in the opposite direction?
Yeah, exactly. A and B, I just keep showing that A is positive, but no, you can flip both. Yeah. Yes?
So on the left one for the A plus B, if
Mhm.
you did B first, like you went to the diagonal and then you added the A, you'd still arrive at the same point.
If you get A first.
Well,
Oh, you mean
B
here.
first, yeah, on the left diagram, if you drew B first.
Oh, yes, it will be the same. Yes.
Yeah.
So you can mix the order A plus B, B plus A, and then subtraction also can be changed. Minus B plus A also will be the same. Yeah. Does that make sense? Does it answer your question though? Yeah.
Yes. Thank you.
Nice. Very good question, people. Very good questions. Finally, this is pretty cool also. You don't have to write it down. However, check it out how awesome this is. Let me show you how to draw this. We have A. That's from the parallelogram rule. We have B. Now, we just learned that A plus B will be diagonal. You recreate B parallel to B, and then A was here, so now we're going to recreate A parallel to A. That creates a beautiful parallelogram. A diagonal, like we mentioned, is a sum. That is a sum. Starts at the beginning, points to the ends, right? So all the beginnings are together, all the ends are together. That is a sum. We just learned that, called parallelogram rule. Well, the subtraction will be the other diagonal. The subtraction will be the other diagonal. But now the question is which one? This one or the other one? It points to the positive. It points to the positive vector. If A is positive, it better point at A. So the other diagonal is a difference. It all comes from geometry, which is kind of interesting. Vectors have deep connection with the geometry. Basically, A plus B and A minus B are diagonals of the parallelogram formed by A and B. Do you know how to say diagonal in Russian? I like your guess. Diagonal. I just freaked out for a second and I forgot. Sometimes I forget. Very funny. Move on. Let's do, what does it mean to have parallel vectors? That's very important. Parallelity means they never intersect, blah, blah, blah. So how to figure out parallelity, especially in magnetic field, it's very important. Lots of stuff is parallel there. Flow, air flow, and so on. Look at those two vectors. Do you see something interesting? A is 1 and 2, B is 3 and 6. Well, seems like there's a connection between them. B is 3 times larger than A, right? If I multiply by 3, it will be 3 and 6. So I can write it down that B is 3 times A. That literally takes you to the definition of the parallel vectors. If you can figure out a scalar, like it's called scaled, which gives you another vector from the first one or all of them, that means they are parallel. It means they stretched or shrinked, but they go to exactly the same direction. So Here's the visual. First of all, let's check that this visual. Well, let me show you. First, A is this one. B is the same one, but 3 times longer. 1, 2, 3. But they are parallel. They're pointing to the same direction. Let's check. You know, I never trusted those pictures. What if it's not the correct vector? Let's quickly check that A is indeed 1 and 2. Visually, it should make sense. Let's see. 1 and 2, let's review it, whatever I said half an hour ago, is 1 unit to the right and then 2 units up. Yeah, it makes sense, you see? So 1 and 2 means tilted a little bit to the right, but tilted twice more up. Yes, this vector is indeed 1 and 2. Then the other one is 3 and 6. Let's check. It should be 3 times more to the right and 3 times more up. So this is 3 and this is 6, which is twice more than to the right. Yes, they are parallel. It just stretched, but they still have the same idea. Tilted to the right and then 3 times more tilted up. Gives you the same vector, but with different magnitude. This vector is 3 and 6. Can you give me any other vector that will be parallel to those two? C. Any? Yes, anything. There's infinitely many of them. 9 and 18. How did you get 9 and 18? Multiply by 3b, yeah? 3 times 3 is 9, 6 times 3 is 18. Good job. Let's try to draw it. 3 times 3 units to the right. Let's do it in blue. 3 units to the right, and then, not 3, 9. 9 units to the right, and then very high up. Well, it's still the same. You see, it's worked. I don't want to go too far. Still, you see, it worked. C equals 9 and 18. Can I divide by 100? Yes. If I divide by 100, it will be 1 over 100 and 2 over 100. It will be super tiny, but it will be parallel. So, and so on. So that's how now you know how they look like. Write down a definition, though. A and B are parallel if B can be written as C times A. You see, no bars, it's kind of hard to visualize it. A and B and A are vectors. C is a real number. And you can do the other way around. A is C times B, whatever. It's called scaled. The question?
Yeah, this still applies when there's a Z value as well, right?
Yes, exactly. Thank you for asking. We're going to have 3D, 4D, 5D at some point. So all of this applies to all dimensions. Yeah. Very good, actually. I can write down since you guys are writing anyways. A is 1073 minus pi, right? You can create B. Let's multiply by 2 everything. Let's multiply by 3 because we already did 2 before. 3, 0, 21, 9 minus pi. 2 vectors are parallel. I wanted to make sure this word is written. We officially say bar. See, I'm getting lazy at putting bars instead of vectors. That is okay. So you'll see bars and vector signs. Let me say something. One vector is scaled towards another one. So this is official term they use, scaled. Scaling means multiplied by a scalar. Scaled. Yes?
It's got to be negative 3 pi, right?
Maybe. Yes, good catch. I did it on purpose to see if you're paying attention. 3 pi. Good job. Good catch. So I always have some, usually I always have some very quiet students in class who just never say anything until I make a mistake. Very interesting. And I always see that that's one person, or those are 2 people raise hand, like, oh, if Jacob is raising hand, or if Samantha is raising hand, oh, that probably I messed up. So there's always some person. Very convenient. It's very good. You have to fix all your professors. Some of them get angry about it, which is wrong. They should not. Having good notes, for me, it's important. Like, good notes should be good. No questions. No extra uncertainties. That's my point. Yeah? So it should be good. So, scaled. One is scaled towards another one. And then, you will have your homework like that. Can you tell me if in A, are they parallel? 2 and 4, minus 4 and minus 8. Parallel or not? Yes. Scaled by what? -2. 3, 5, 2, 9. No scaling here. They're just completely different. 1, 5, 2, 3, 15, 6. Yes. What is a scalar? 3. And you can check all of them by drawing quickly. For example, the second one, if you want to check visually, you can. You can just draw 3 and 5. 3 units to the right, 5 up. It will look something like this. But now 2 units to the right and 9 up. It looks something like this. Yeah, for B, they're not parallel. So you see visual supports algebra. Like the first approach is algebraic approach. You just see if you can find a scalar. The second one is geometric approach. You actually visualize it. And it supports, indeed, for B, they are not parallel. So I can give you those notes. You don't have to write it down if you don't want to. Or I can wait. But that's just simple exercises. You can do at home. Let's learn something amazing and new, which is super important, which is lengths, how to find magnitude of the vector. Another special operation you can do to a vector is to take its lengths. To find the lengths, let's write down the formula first. So write down the lengths, that's in chapter, whatever, magnitude. The formula for the magnitude is magnitude. Notation is double bar A, double bar, equals the square root. So magnitude is a number. Just important to point out. Soon you will be very confused with all of those things. What is a number? What is a vector? In this case, remember, it's a size, 5 feet, 7 kilometers. So it's a number. And then you do all those, let's rename it to V, so I can use A and B. A squared plus B squared plus C squared, and so on. Where V, as a vector, has components A, B, C, like so. Are you slowly zoning out? I feel like it's hard to pay attention for so long. Yeah, try to wake up. There's a phrase I learned. If you zoned out, this is an important moment to come back. Like, come back. Magnitude is extremely important. We're going to have magnitude in the first, second, third, and final exam. And you will have it in other classes. It's actually very cool. You will see all those things in physics classes you're taking, in engineering classes. You will see vectors everywhere. Magnitude will be everywhere. That's the size of the current. That's the size of the blood flow. Magnetic strength of the magnetic field. That's magnitude. Yes?
One of my past classes, I talked about length being the magnitude, the vector dotted with itself. Is this the same?
Yeah, we're going to write it down. Thank you. Don't spoiler. But yes, exactly. Spoiler alert. Yes, exactly. Very good. I like when people bring stuff from other classes, especially the classes I don't know. So if you bring something from physics and chemistry, it'll be fun. A times A, exactly. So very simple. The beginning of this idea is super simple. Let's find the magnitude, the length of A, if A is 1 and 2. Well, guess what? A magnitude will be a square root of 1 squared plus 2 squared. That is square root of 5. So this homework will be very fast at the beginning because they will ask you to find a couple times. No tricks here. I don't even care about negative signs, you know. Negative signs in the vector component tells you the direction. Oh, it goes to the backwards or forward, left or right. Yeah, it's a size. I don't care where it points. So that's why when you square it, the negative signs go away because they get squared. So I don't even care about that. Very cool idea here. I don't care if it points this way or this way. I'm caring about how large it is. It's a number. So that makes it very fast to calculate. It comes from the Pythagorean theorem, which I don't really care to explain. I mean, we all remember how it looks like. In general, you don't have to write this down, but in general, as many dimensions as you want. You just find the lengths exactly the same way. The huge square root, square all the components and add them together. The interesting point, I copied from the Wikipedia. So it's called Euclidean distance. That's a Euclidean norm of a vector. It's a special case of Euclidean distance, the distance between its tail and its tip. Unfortunately, the world did not agree on the notation for that. You will see in the book the double bar, and you see in the book 1 bar. But 1 bar is reserved for absolute value. But absolute value is also a length for some notation, so it's not contradicting to it. So when I went to Wikipedia, it says, yes, different cultures use different notations, either that one or this one. So I prefer the double line, but if you don't do it, it doesn't matter. Just do one of these. Don't keep it naked. It should have something, either double bar or 1 bar. But both are legal. You'll see both in different books. Okay, who can find this for me? I'll wait a little bit. Find the lengths of A, 1, 2, 4. Wow. You just add it up. That is fast. Thank you. Let's write down nicely so you remember the notation. Double bar equals square root of what? 1 plus 4 plus 16. Good job. What do you say was it? 21. So that's going to be the pleasant part of the homework, basically. Not too bad. Now, very interesting part comes from this. What if I want to get rid of the lengths? Let me justify first this idea. And I think you're falling asleep, so I'll show you some cool animations. Why do we need that? The thing is, if you work with magnetic field, for example, or flow, like right now California has this storm accumulating, all of the things you see in the internet, those colorful, beautiful things, those are vector fields. So we see vector fields since being kids in the news, just nobody calls them like this, but that's exactly what they are. The thing is, sometimes we don't want to see the lengths of them. We want to see the pattern. Where do they go? In the sink, will it go this way, counterclockwise, or this way, right? To get rid of the lengths means to unitize the vector. So let's keep them all the same size, 1. So I just only want to see where do they go. So that is a pretty cool notation that looks like this. If I don't need lengths of the vectors, I only want to see the direction. When I drop an object on that vector field, I want to see where it's going to go. And as you can see on this animation, it actually even transforms the object, transforms the shape of it. More magnetic fields. As you can see, all of them actually have the same size. I don't see a huge one or a tiny one. That helps me to visualize the pattern. Where does it go versus how strong it is? If you want to see what is a strong one, then how do I know who is the strongest if I don't have any lengths? Coloring helps. That's called heat maps. When we add colors onto the vector field, that's called a vector field because it's field of vectors. All of these vectors have the same lengths, 1, and we're going to learn how to find them right now. But coloring helps me to know where is the strongest vector. The red one is the strongest, for example, or the blue one is not, and so on. Some 3D representation of vector fields, how things are moving. Also, color coding helps me to see different patterns. Is it water and oil moving? Is it your blood and some fluids together mixed? Which one is which? Yes?
For the previous animation, could you tell just by where the arrows are pointing how strong it is? Because
if they accumulate together, so the question is, can we tell it without coloring? Sometimes yes. If the vectors are accumulating together, of course, you can see the blood is moving left and right, but then most of them pointing towards the center. Then yes, it's going towards the center. So very clever point. Sometimes it's not obvious, so they make those errors, or sometimes it's just very pretty. To be honest, when computer science show up and we were able to code all of this in Python and R and C++ and Java show up and so on, people were very excited. I clearly remember coding your first graph as a graduate student. You show it to everyone, people super excited, like, wow, it looks beautiful, especially if it's your research. So I think most of the time it's actually just because it's really cool. Not actually necessary, but many times it is necessary. But this is exactly what you're talking about, I think, right? Check it out. There's no coloring, but you can see which vector is stronger. That's a magnetic representation, see? Vectors here have magnetic fields. And you can see, someone actually coded, some student coded this. you can see which are stronger. They accumulate together a lot. When they crumble together, that means they're increasing the flow. That's pretty cool. So this is the coloring version of the same thing. Now it's kind of more visual, but you're right, like you could guess without it. But yes, red color represents it's very strong, blue not stronger than other colors, and then the outside, the magnetic fields. Let's see if there was something else. Okay, that's good enough. So that's fine. Let's learn how to find that. Let's learn how to get rid of the length or magnitude of the vector. Check it out. It is very useful to produce vector of length 1 called unit vector. So let's write it down. Unit vector. Unit vector. We're going to be asking you to find it for the whole 4 months. It's extremely important. And you will see it everywhere in other classes. Unit vector doesn't have really notation. It just has a formula. You take your vector and you divide by its length to get rid of it. So basically we are scaling the vector down to size 1 or up if it was tiny. We want to get rid of its length. So A over A, that's how I like to say it. A over A, but actually it's vector over length. Let me write it down. Vector over its length. Over length. So it's called unit for a reason. It's a unit point. Units of some measurements means original 1. So it has length 1. That's the whole idea. Let's practice that. If A, example, if A is 1 and 2, then let's find unit vector A. They will ask you, find the unit vector A. Find the unit vector A. You literally need to know one formula. That's it. A over A. Vector A over size of vector A or magnitude. And now you just actually proceed with calculations. So it has 2 steps. Step 1, find the length of A, because you cannot divide by something you don't know. And then step 2, actually perform the division. So let's find the magnitude of A. We just learned the square root thing, the square root formula. There's a square root, 1 squared plus 2 squared. That gives you square root, let me, I guess, write it down so you have good notes. 1 squared plus 2 squared. That is a square root of 5. So now we know the length of the vector. We want to get rid of it. Step 2, divide by this length. So we will have vector A, let me put it in blue, vector A over size of A. That's the formula. So the denominator is the square root of 5. We just found it. But the numerator is a vector. And we actually never discussed how to divide vector over a number. Yes. How to divide vector over a number. It was square root of 5. Exactly. What if we just see it? Let me check the time. Still getting used to it. 10:15. Good. What if we see it as a product, right? We know how to multiply by 2 or minus 1. So we know how to multiply by 1 over square root of 5. Amazing. Good idea. Thank you. So we're going to do that. It will be 1 over square root of 5 times 1 and 2. Oh, I changed the colors accidentally. Well, whatever. Fine. Let's recolor it. Oh, and square root. Thank you. Let me change this to be green. Good. Oh, it's slowing down. That's why. See, my computer cannot handle long lectures. But I got a free computer from the department because I asked. Honestly, sometimes you just need to ask. And I asked, and they asked me to justify it. I said, well, my students told me it's too slow, which is not true. Students did not complain, actually. And they said, well, they talked to the department, they renting me a new computer for like 3 years. Yes. So I'll start using it next week. It'll be much better. Now, we're just gonna multiply it component by component, and that is the answer. Equals the answer will be 1 over square root of 5, comma 2 over square root of 5. So let's see what's happened. We had the original vector A, draw this picture. Original vector A, like so. A was 1 and 2. And then we did not like that it has a length. And the length was square root of 5. So the whole length of this vector was square root of 5. We did not like that. We wanted to find the unit vector for A. So we wanted to shrink it to size 1. And we did by dividing each component by the length. So 1 was divided by square root of 5 and 2. That became the same vector. It's parallel because we're scaling it. It's parallel, but it is size 1. In this problem, we always justify at least once for students. Is it true, though, that this vector has length 1? So let's do that. My claim is that the unit vector we just found has length 1. So let's check it. Check. We know that size, magnitude of the unit vector better be 1. That's the whole point. That's why it's called unit vector. We know that. So let's check that. We want to check the size of the vector we just built. 1 over square root of 5, comma 2 over square root of 5. We want to find the size. See the notation. I'm making a mistake, maybe on purpose to point this out. There's a bar on the right. It has to be a bar on the left. Not bar, brackets. And then bars on each side. Inside bars or brackets, I'm indicating a vector, and then outside bars indicating magnitude. If you don't be strict with notation, it may be an absolute value of a number. That's not the same formula. Well, it's a square root. It doesn't look like to be 1. You see, I don't believe it. It doesn't look like it's going to be 1. Let's check. 1 over square root. So it's a square of 1 over square root of 5. That's 1/5. And then 2 becomes 4/5. Oh, yeah. It is square root of 1. So it's 1. Make sense? That is what's happening here. So you always can check that if you messed up. On a test, we're going to ask, it's probably going to be the first problem of the exam. Find the unit vector. And you can always actually just find the lengths from A, B, C, D. And that unit vector have to be 1. Have to have length 1. What makes this special is that the new normalized vector, it basically has a unit, it's unitized, unit 1, has the same direction as the original one, but now it has length 1. Same direction, but smaller magnitude in our case. See, that's my example for you is, for example, magnetic field and so on. I don't need to have lengths of them. I just want to see where the current is going. Yes?
So for these examples, are you using length and magnitude interchangeably?
Exactly. That's actually I'm doing on purpose. Thank you for asking. Magnitude and lengths, I keep saying both. That's the same thing. Yeah. Magnitude and length. And sometimes people say size. That's the one I don't like. Yeah, length is actually how long it is. So I like that. Yeah, that's the same thing. Good question. Now I'm going to ask you something, last important thing. Okay, first of all, there's a joke. So let's wake up for a joke. Look at this cool meme. We taught you absolute value in school. That is 1 bar and x. Magnitude. I like to use 2 bars, but actually it is legal to use 1 bar for the vector, right? Now, unit vector is v over v with the bar at the bottom. What if I want to find the size of the unit vector? And now imagine if I actually have double bars everywhere. This is a double bar and this is double bar. So that's like the final stage, okay? The final stage of this madness. The magnitude of the unit vector, but unit vector is v over magnitude. So that's why it's keep accumulating, basically. That is funny. I like this one. Let's see. This class will have extra credit for the best meme in the class. I will post it later in the forum. That's not a joke. Last semester people got the extra credit. It was funny. So that's just some intro. I like good jokes if they connected to the class somehow. But no bad language, please. That's important. Sometimes mine will not understand it. That's what I'm afraid. And then people will say, oh, Professor allowed some bad stuff. I might not just to get it. So try to avoid bad, weird jokes. Don't, because I might not understand it as well. Finally, the last important thing, and we can go, is this. This was a very funny joke like 2 years ago. Name a better trio. And do you know this meme? It was like super not funny meme at all. But the fun one was that actually it has continuation in vector calculus. I just was too lazy to find the continuation. This is a continuation. The most famous trio in the world is IJK trio. Literally everyone know it. They call it standard unit vectors. Let's write it down. Standard unit vectors. Let's not do two-dimensional. IJ actually is not as known as IJK. IJK, standard unit vectors. Extremely important. Everything in the world is described using standard unit vectors. Everything. Temperature, air, magnetic fields, how sweet the chocolate is. All of this is described using standard unit vectors. Even neuroscience, the mood swings, that's what psychology department is working with neuroscience. All of this also uses IJK. So it's classical. If you write in Japan, you go and see people in Japan and you write IJK, they know what you're talking about if they took STEM classes. It's that famous. And it's some connotation is using English letters IJK. I don't know why. So extremely famous. What is so important about them is the construction. I is 100, J is 010, and K is 001. The whole idea here, so you'll need to remember that. This is very, easy to remember, but pretty clever. The idea is draw the 3D coordinate quickly, X, Y, and Z. And then on each coordinate, I have those 3 unit vectors. I is lying down on x-axis, J is lying down on y-axis, and K is lying on the z-axis. So they belong to each direction, and they all have the same size. I is 100, J is 010, K is 001. That means we decided, so if we decide to work with unit vectors, then we can indicate each axis with a unit vector. That is so clever. X-axis is front and back. Let's call I as a unit vector that points towards front and back. Minus I will be back. Y is left and right. Z is up and down. Each unit vector creates the direction in 3D. That is genius. And because it's so genius and amazing, every vector, write this down, every vector can be written in terms of these basic vectors. Sometimes they call basic vectors, but the international name is standard unit vectors. So every vector, that's very important, and that's why they are so amazing, can be written using those 3 vectors. For example, and that will be the last thing to do. For example, we have the vector R. Let's call it R. Here it is. And the vector R has A, B, and C. It's a vector pointing to point P that has coordinates A, B, and C. You don't have to do the graph yet. We will ask you to write it using IJK, and this is how you're writing it, using IJK. A is a scalar that belongs to x-axis, right? So I is a unit vector on x-axis. That means we're going to write it down A times I. I is 1. It has length 1. And then A will be either stretching it or shrinking it. So it's scaling it up and down. Now see the wrong notation, which this time for sure I did on purpose. A and I are different objects. A is a constant, I is a vector. So that is very important to remember. Same with B. B is scaling up or down. Up and down means bigger or smaller. Let's not use this terminology in English. It's confusing. It's scaling the coordinates on y-axis. So we're going to write it down as J. And then Z is a constant C that is scaling on z-axis. So we're going to be using K here. Every vector can be written as IJK. IJK. So In the sake of exercise, and so you can finish your homework, the example 1, 3 minus 5 and 17. This vector has 3 units on x-axis. So it's going to be 3I. I is 1, length 1. And now it's multiplied by 3, so it's 3 times longer on the x-axis. J has size 1, but now it's reversed, minus, and multiplied by 5. J and 17K. That is what they will ask you to do in your homework. Create a vector. Just a second, please don't leave yet. Yes?
So when you're using that, you start to put the thing on top of it?
Yeah, I do both. No, it's not necessary. Sometimes you can, I'm just getting lazy, so I do them or not. But IGK, so vector notation V, either this or that. Both are correct. And I keep switching between them. It's nice to be consistent, but I like using both so you get used to both. What do you think, people? Not too bad? Okay, please start your homework. Yeah, do you have a question here? You can come here. Please do your homework as soon as possible and let me know if you need help. Post your questions in the forum.